Share.
Nice.
It is nice. Thank you all for coming.
All right, so it's my pleasure to introduce Robert Dukes, who will give us a talk on minimal error functions in irregular sets. And that's just going to be his Ph.D. defense.
All right. Thank you, Dr. Zinchenko, Dr. Blair and Pereira and Christensen for agreeing to serve on this. So, I'm going to start with an observation here, which is that polynomials are really nice. When you're first doing calculus, everything's polynomials. You've got derivatives and integrals are really easy. And then you get to harder functions, which aren't so nice. And then you get to the end of Calc 2, and they tell you here are Taylor polynomials, where you can approximate these weird functions with nice simple things. Polynomials are nice because you can do derivatives and integrals. They're nice because they're all adding and multiplying. So you can feed it into a computer, and it can get you nice simple answers. So the question is, are there better polynomials besides just the Taylor polynomials? And that's where we're going to start this. So we're working on compact sets in R for this talk. We define the supremum norm as just the largest value the function takes over the set E. So if it has just one exceptional point where it gets really big, that's enough to make the supremum norm get much bigger. So then the Chebyshev polynomial of degree n, we're defining as a monic polynomial, which we'll write Tn. Chebyshev is sometimes written with a T, where the supremum norm is less than or equal to the supremum norm of any other polynomial. And that number, norm of Tn, is called the nth Chebyshev norm. Now this norm might get very large, depending on the degree, depending on the complexity of the set. So we define this Chebyshev constant, which is the limit as n to infinity of the nth Chebyshev norm to the 1 over n power. And that has the convenient property that is always going to exist as long as we're dealing with a compact set. And so our goal here will be to figure out how big these are and do they go to infinity or not. So there's a useful property here that characterizes these. It's called the alternation theorem. We have a compact set E. We say the polynomial has an alternating set if there's a set of points, n plus one of them, one more than the degree, where at all those points, it takes the same value plus or minus. So it'll go up, down, up, down, up, down. We can see from this, here I don't know, not at home it's this, but the points are marked down, up, up. So these are the Chebyshev polynomials on the set -1 to 1, which is the classical example. That's what Pafnuty-Chebyshev first worked on. A single interval. And if you look at that, you can see the shaded points there. So the way to think of this kind of in a very informal way is that if you had one peak that was higher than the others, it's kind of wasting force there. You might think, I mean, this is very informal, but then what you would do is you would say, well, I'm going to add in a smaller degree polynomial that kind of redistributes that overly large peak to all the other ones. And you keep doing that until all the points, all the peaks and valleys are at the same height or depth. And once you have that, that guarantees you that there's no polynomial that could beat it. So it's a really convenient test. If you can see these up, downs that are all the same height or depth, then you know you have the right polynomial. And this simple theorem has a lot of really nice geometric implications. For example, if you've got these n plus 1 points that are max and mins, then that means there have to be exactly n zeros. It switches sign n times. They'll have to be real zeros. They'll have to be simple zeros. Again, we're still assuming E is a subset of the real line. And the derivative can only change. Yes, derivative can only change signs at those max and mins. That's where it would be 0. So therefore, in between them, it must be monotonic. So what we get then, this polynomial, we have the points, I said, the up, down. Well, they'll have little paths where it'll go across the range of it exactly n times. And those are called the bands of En. I think of En as the cousin of E, where they have a common ancestor, which is if you apply T, the polynomial, you get some numbers in the range, and you go backwards and you get other numbers that would give that same value. So we're saying that E, all we know about E is it's compact. It could be an extremely messy set. But En will just be a collection of n closed intervals. They might butt up against each other and share endpoints, or they might have gaps between them. But it gives us intervals, which are easier to work with. So remember that En is just all the bands going up and down. Well, it's the pre-image of those. Now we also know about harmonic functions, and if you've taken complex analysis, you know these a little. You did them a little. I remember asking Dr. Blair back as undergrad or in my first year, what are these used for? We talked about them and they never came up again, but now I see them all the time. So Laplace, he said, we want an equation where the second x derivative plus the second y derivative is always 0. And these represent functions, they represent a fluid flow that has no sources or sinks. If you take multivariable, you know, there's the test, the first derivative test, which would show you that a max or min, this could not be a max or min if this is true. So the electromagnetic field generated by a charged plate is an example of this. The field lines that it throws out, they will not have any sources or sinks outside of the plate itself. So we have this, we have if we have our function E, and we know a function f is continuous on that boundary, then their Dirichlet problem, or Dirichlet if you're French or German, is to find an extension of f that's harmonic on E complement. So we have our set E. Now, sometimes it'll be the interior E. Since our E is considered a subset of the real line, its complement, we are describing its complement in the complex space. Meaning what you want to imagine is some little subset of R, some intervals, maybe some isolated points. And then hey, you got it. We want it to be harmonic everywhere else. We got a little set in the middle where it's known, it takes some given values, and we want to say, well, we want it to match those values and be harmonic everywhere else. And problems like this lead to Green's functions, which if you've taken PDEs, you know about, and you may know more than I do about them, but we're going to focus on a specific case. But first, we're going to talk about the mean value property. So the mean value theorem says that you have a harmonic function, this is one version of the mean value theorem, that's on some open set. And you can fit a closed disk inside that set then the average you get by integrating around the outside of that disk and divided by 1/2 pi is the same as the value at the center. But what if that's not the case? What if we can't fit an open set around our closed set? Or what if our set goes all the way to infinity and the boundary is hard to define? Well, we come up with this new measure called the harmonic measure. This took me a while to figure out. This is just a generalization of mean value theorem. I remember I figured out like 1 a.m. and immediately ran to my notebook to write down the notes. Not that my dad was asleep on the couch. We gave each other a good scare that time. But so what we are saying is with our compact and non-polar set, I haven't defined non-polar yet, that's out of sequence, but we'll get there. If F is continuous on the boundary of E, and since our E is usually in the real line, it's its own boundary, there's a unique function that's harmonic on the rest of it. And here's the Dirichlet solution here. The limit, if you're approaching any point in E from outside of E, is the same as that value. So we're not necessarily saying that it's equal, but the limit exists, and that kind of extends it. And if you evaluate this at infinity, it is the same as integrating the function along that boundary with respect to this new measure. So we've invented a new measure, and we're going to, it can prove that it must exist, where the mean value theorem would say we'd evaluate at the center of the disk. Well, our disk goes all the way out to infinity in this case, so we're going to think of infinity as being the center, and we're saying the value you give this function at infinity is the same as the integral along the boundary. But you have to create a new measure to do it. You can't use the Lebesgue measure. Now we're going to find Green's functions. I have this window here as difference to George Green's day job as a miller, which is now a historical and science museum in Nottingham. I aspire to go there someday. But when E is an R, we can characterize Green's functions by these three properties. First off, it's going to be harmonic everywhere except for E. Second, the limiting property. If we take the limit towards E, we're going to get 0 for quasi every x in E. That quasi every will be important, which we still haven't quite defined what that means, but it's going to be most of it. And third, the difference between log of z and this function is bounded, and in fact gives you this new thing called capacity. So the Green's function will look very similar to log of the absolute value, log of the distance near infinity. And this new quantity C of E falls out of it. What is C of E? Well, it's called capacity. It's kind of like a measure. It's not actually a measure, but it's the same idea in that it kind of represents how big sets are. It's monotonic under set inclusion. If A is contained in B, then capacity A is less than or equal to capacity B. And when the set has capacity 0, it is in some sense negligible. And that's called a polar set. So I'm going to give a really quick rundown of what the fundamental theorem of classical potential theory says. And so this is not the only way to derive it, but it's a nice physical intuitive way, which is you have a pen that is, and you put a bunch of marbles in it that have all the same charge on them, they will push each other away. How far away will they push each other? Well, we're working in 2 dimensions. What happens is that they will maximize the geometric mean. geometric mean. Those are all the distances multiplied together to the root equal to how many distances there are. It's a handshaking problem. So you can see in the example here, if you look close on those circles, they're at the roots of unity of the circle. And if there was a lumpier set than a circle, then the exact distribution would be a little tricky to find. I think that's a place where a computer might be helpful to track down what are the highest geometric mean. But we can see this has an upper bound. As you fill in, it's going to approach some quantity as we continue to add the number of marbles. That's called the transfinite diameter. What's nice is it is the same as the Chebyshev constant we said before, the nth root of the nth Chebyshev polynomial taken to infinity. The norm of it, sorry. Nth root of the norm of nth Chebyshev. And it's the same as that capacity we just found from the Green's function. There are three different ways of saying the same thing. And even better, you can use the counting measure on these sets, they're called Fekete sets, and you can approach the harmonic measure we had above. Another property of harmonic measure is that it is the lowest energy measure, but energy is something I'm not going to try to go into right now. Energy minimization is the theme of a talk of a session I'm going to in May at Vanderbilt. So anyway, this gives us our key. This is our Rosetta Stone here, that the capacity, which comes out of Green's function, is directly linked to the Chebyshev constant, which is about polynomials. Transfinite diameter, I just put in there because it's a really visual, really clear way to show how you would find this in practice. So now that we have this, we're going to say what is the solution for the Dirichlet problem here for E and R. Okay, so this is combining a few things we said before. We said that reproducing property, which is to say, well, we'll create a new function. We'll create a function that's h of z, which is the Green's function on E minus Green's function on En. Remember, E and En are two separate sets. E is a subset of En. And so we're just defining this new function that's the difference between them. Well, this thing is going to have to be 0 on E, or most of E anyway. And it's going to go G of E on En. That is, when we're on En, the Green's function for En vanishes, so we're left with just the Green's function for E. When we're on E itself, they're both vanished, so it's 0. With the exception of some scattered points that we'll talk about a little later. So then that reproducing property kicks in. This is the Dirichlet solution. And so then we can evaluate infinity. We can say that this integral is the same as h valued at infinity, which is g of e infinity minus g in infinity. All right, so the difference between those two Green's functions is going to come in handy. So now we're going to introduce the main thing we're trying to investigate, which are called the Widom factors. Why are you throwing in yet more terminology? Well, because the sets we're dealing with are, I'll be really careful here, they are sort of scale invariant, sort of. If we're dealing with intervals, for instance, capacity is always 1/4 of the length. So for more complicated sets, it doesn't scale quite as nicely, but it's still increasing the size, will increase the capacity. And so we just say, well, let's divide out capacity to the n power, just so that we're dealing with the shape of the set, not the size of the set. And so then Dr. Zinchenko and his colleagues used the Perot-Whittam constant to deal with regular sets. Did you coin that, or was that pre-existing?
Well, it was existing, yes.
Okay, well, they used it anyway. So what this is adding up what the Green's function evaluates to at all the its own critical points. Now, the point of that is that we've said that Green's function is 0 on this defining set E. So if E were just a single interval, it'd be 0, and then it would go up as you went away. There wouldn't be any critical points. The Perot-Whittam constant would just be 0. If it was 2 intervals, there'd be one gap in the middle where it would go up and come back down, so you'd have 1 critical point. Every time you break up into more intervals, you get more critical points because it has to keep going up and come back down to 0. So this is kind of a measure of how many intervals there are. Again, I'm being a little informal with that, but this is the strict definition is you sum in all the critical points. And with that, there is some existing results. So Frostman's theorem, this is also sometimes called the fundamental theorem, depending on which one you think is more important, which is to say that the Green's function is going to be positive on all of the complex plane and 0 on all but a capacity 0 subset of E. So we are frequently going to be switching between thinking of living on the real line and living in the complex plane. We say set is regular if it's 0 for every point in E. So Frostman's theorem here, it allows a few exceptional points. The one common way to think of it is if you have a charged plate or charged bar, you have a bunch of little extra spots, extra little specks of metal throughout the thing. They're too small to hold the charge. So, what do we know? Well, we know that the Whittam factors are always at least 1 for any compact subset of C. If we shrink down to subsets of R, we know that there are at least 2. If we then say, what if they're regular subsets of R? Well, we get an upper bound, which is 2 times the exponential of this Perot-Whittam constant that we just described. And then you could combine the second and third bullet point there and see that the Whittam factors are nestled between 2 and 2 times that exponential, because the Perot-Whittam constant is always non-negative. If it were an interval, the Perot-Whittam constant is 0, and so it would just be equal to 2. So that, when I came upon this about 3 years ago, was the state of things of understanding for regular sets. And I said, well, what about those irregular sets? What if there are points where it doesn't equal 0? How will that affect it? And Dr. Zinchenko said, good question, go figure that out. And that's what I've been doing for the last 3 years. So just as a warning to those of you who are starting off, like Leon, be careful with hypothetical questions. Or rhetorical questions, whichever. All right, so let's talk about why that is. Well, okay, we have a set E, and we can split it up, partition it into 2 parts. E naught will be the part where the Green's function is 0, and E plus will be everything else. Frostman's theorem says it must be positive those other points, so that's why I'm writing plus. Now this little chart here, this little diagram, in red is supposed to be a Chebyshev polynomial, hypothetical one, drawn not very well, I'll admit. But the Green's function here, you can see if I've got an E naught and E naught, different intervals in there, the Green's function is 0 there. It's just ignoring all those isolated points. It doesn't notice them because Green's functions are unique up to a set of capacity zero, meaning if you just add in a few extra points that are capacity zero, it won't change Green's function. Chebyshev polynomials care a lot about those isolated points. And so they have to sort of dramatically swoop down to touch base at or near every single one of them. And so you kind of get the idea that as you add in more of these isolated points, you have more of these dramatic lunges up and down. They're probably going to start getting larger. They're probably going to do in between. They're going to overshoot it quite a bit and make the Whittam factors get much larger. And that's the key idea here. So I came up with it in the regularity coefficient. It turns out you just add the Green's function value at every point where E is positive, at every point in E plus. And if E plus is uncountable, then we'll just by definition say it's infinity. And we came up with this other idea called semi-regularity, which is that the E naught part, the part where it's zero, is closed. This avoids a lot of pathological cases. For one thing, we want to be able to say what is the Green's function on E naught. Well, the way we define Green's functions was with a closed set and being harmonic on the open set that's its complement. If it weren't closed, we might be able to work around that, but it would take some extra work. If E naught is not closed, it will be the Green's function will be discontinuous at its boundary points. This is a theorem that on the supports of the harmonic measure, any point where it's continuous, it will also be zero. So we get discontinuities. And if we know it's closed, we can say that E plus has a limit point E plus, or every point is isolated. And being able to, that allows us to enumerate the gaps, which is something we want to do. So this semi-regularity thing was a necessity that we invented, and it would be nice if we could somehow work around it. Other cases where that's not needed, but for the moment, we're not there yet. So we're going to, so keep this in mind then for the rest of this. We're dealing with E naught is closed and E plus is, generally speaking, it's a scattering of isolated points most of the time. All right. So now we're going to start talking about the bounds, and here's where new material. Everything up till now has been prior material. Now we're talking about the original results. So, if E is a semi-regular compact set E, then for all n, W and E, the Whittam factors, are bounded above by 2 times the exponential of Whittam constant plus the irregularity coefficient. So you'll notice this is exactly what was given before, just with this IRE added in. So why do we do this? Why do we know this? Well, there's a few steps here. Our reproducing property we described says that we can get a closed form if we integrate over the gap, the En, not counting E, of the Green's function to be with respect to this harmonic measure. Strictly speaking, we could just say integrate over En, because if we were to integrate over E, the Green's function of E is 0. So we're just, the way it's written is just cut out the gaps where it's 0 because they're not relevant. So infinity is the limit as n to infinity of that difference. Might have mixed notation. G sub n is G sub En. Now we know that Green's functions are always approximately log absolute value z near infinity. So as we go to infinity, those parts cancel out, and we end up with a finite value, which turns out to be the log of capacity En over capacity of E, which works out to log of the Whittam factors over 2. And you can multiply that out and take the exponential, and you get So we have a bound there. Now the integrand is 0 on E, so we'll integrate on the gaps of E. So we split up En into gaps. Assuming we have countability, the right-hand side there of this integral of this inequality would be the sum over each gap of the integral over the gaps of the Green's function. Now it is given that the measure of each band is 1 over n, and so each gap could contain a band or contain part of a band, but it could contain more than one band, which is a separate proof. So we get the measure is 1 over n. So we're saying, what's the integral over one of these gaps? Well, its measure of the gap is 1 over n, and it must be less or equal to its own maximum. So we get that 1 over n times the sum of the max over each bound, over each gap, sorry. Now each gap's an interval, so as anyone Calc 1 can tell you, student can tell you, well, should be able to tell you, the maximum is either a critical point or an endpoint. If they happen to share a maximum, that would mean they'd have to have a shared endpoint in the middle, so it would get double counted. But that's okay, because our sum would also double count it. We'd add up all those points, critical points and endpoints, value of the Green's function, all those, and we get this new sum. That's our upper bound. So the upper bound stuff is largely an extension of what Dr. Zinchenko and others have already published, with this new question of what about the irregular points. It's a very similar proof. The lower bound was a lot more original. So we have a compact semi-regular set E. We show the lim nth of the Whittam factors is at least 2 times the exponential of the irregularity coefficient. Right? And so I show another picture here with a smattering of isolated points, and we can see the function swooping up and down to try to touch base with all of them. Increasing the degree will increase the steepness, and that will cause the norm to increase. So I'm going to give a rundown of the proof here, and this is where we get a little more advanced, but I like the Bernstein-Walsh lemma. It's a really nice piece of work here. It says that any polynomial in degree, we have a compact set E, we can say that wherever it is, it's bounded by its own Chebyshev norm times the exponential of n GE. So if we were on E itself, the Green's function would be 0, and that would just be the definition of the supremum norm. And then as we go away, this extra factor gives a growth rate as we go away from there. And so a consequence then is if we take the Chebyshev polynomial and take its nth degree, it's going to converge to just capacity times the Green's function. That imagine replace that Pn with Tn, put a 1 over n there, get Tn to the 1 over n, that goes to capacity. And the nth root will just drop that in out of the exponential, the Greens. And so as long as you don't have any zeros in the set, there's a divide by 0 thing that comes up. So as long as you don't have any zeros in there, this convergence is very nice. This is kind of what I've said several times, but I'm reiterating it. But Chebyshev polynomials have to touch base near every isolated point of E. So as the degree increases, the zeros will approach every isolated point. So keep in mind, isolated points do factor into the supremum norm. So if the value were very large at that isolated point, it would cause supremum norm to get very large as well. So we have to say, well, it must have a 0 Zero must be near that isolated point because otherwise it would be too big there. And that previous inequality would cause it to get very large. So, yeah. So you've got all your isolated points. If you had a third degree polynomial, it might just pass through a whole bunch of them all at once. But as the degree increases, it's going to have to keep going up faster and faster to hit every isolated point, and it's going to have more and more turnarounds. So as the degree increases, every isolated point will be the limit of the sequence of zeros, maybe two zeros, but at least one. And what happens there then is every band starts to get narrower and narrower. So our end game is that every isolated point will have a very narrow band around it where it quickly goes from the minimum to the maximum, and then possibly overshoots in between the isolated points. Once we have that, we say, well, what do we know about the Green's function? Well, again, we're using the Green's function for E naught. That is the same as the Green's function for E. And it is continuous. Green's function is not necessarily continuous on its defining set, but it is continuous everywhere else, and even harmonic. So on E naught complement, which includes the isolated points, we have a continuous function. What do you know about continuous functions? Well, if you want to set an epsilon, you can set an. If you want to set an epsilon width, you can get a delta that makes it get that close. So therefore, as our bands get narrower and narrower, their heights, their ranges will also get narrower. And so we can essentially use the value at the isolated point as an estimate for the value on the entire band. And so then we pick some m of them, you can say, well, let's make it error of epsilon over m. Then for large n, and this is the large n part is why it's only a lim inf and not a full limit, or not for every value of n, I should say. But we get that this quantity, log Tn to the 1 over n over 2 times capacity, similar to before, we're going to say, well, the lower band is going to be the sum of the integral over each gap, which would be, in this case, the minimum of the Green's function times the harmonic measure for En, not for E, but for En. Which is good because we know that the harmonic measure for En, each gap, I keep mixing up gaps and bands. Each band has a measure of exactly 1 over n, exactly 1 over n. Yeah. And so then do a little algebra, blah, 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 and you get the results. The Whittam factors for E are at least 2 times the exponential of IRV. Now, that was the most complicated case in a way, but also the simplest case in a way. Well, we were assuming, and I don't know if I stated this explicitly, but we were assuming that that there were no limit points in E plus. That was the assumption we were dealing with. We were kind of relying on the idea that we could separate out all the points in E plus to be isolated. What if we can't? Well, if we have a limit point in E plus, then there's a subset of E plus, and we'll just apply the previous result to that. This is what Dr. Blair calls a bootstrapping argument. We're going to take what we did before and use it for this new part. So we've got infinitely many isolated points. They'll get infinitely dense around some point x prime in E plus, but we can get some countable subset that approaches them. And then we do basically the same thing as before. Each of the isolated points, so our smaller set k, we would get the log of W and K over 2, bounded below by Green's function, bounded at every point. which would be the IR of K minus the Green's function at one X prime, because we're trying to cut it out. That's constant. So the Woodham factor for E are T n of E over C n of E. It would decrease. We are getting E and K are the same except for a polar set, so the capacities are the same. The Chebyshev polynomials can get smaller because it's a smaller set. And so that's greater than or equal to the exponential of IR of K, which will be infinity. And if E plus is uncountable, that's really even easier, because you can do a pretty straightforward topology proof to show that if E plus is uncountable, then there's got to be a limit point in E plus. And so again, the Woodham factors are unbounded. It just collapses back in our previous case. So that's everything for Chebyshev polynomials. Now there is, let's summarize a few things here. So semi-regular per Woodham set, Woodham factor bounded if and only if IRE is finite. Saying it's a Perl-Woodham set just means that the PWE is finite. So this is basically saying if both of those things form the upper bound are finite, then we're bounded. Likewise, if the lower bound were infinite, then the Woodham factor would be infinite. So it's a two-way thing when we do it that way. And corollary, if E plus is uncountable or countable limit point in E plus, then the Woodham factors are unbounded. All right, so then you could summarize these. You could say, given a semi-regular compact Perot-Woodham set E, WNE is bounded if and only if IRB is finite. And if we combine these, we have two E to IREs, less than to the lim n of WNE. Again, we need for large n, so that's why the limit is there. Which does go to the supreme of WNE, which does equal to 2E PWE IR of E. If PW is 0, which means E naught is an interval, then the left hand and right hand side are both 2 exponential IREs, so that's a full limit. Okay, so that's the Chebyshev polynomials. Now I do want to talk a little about a related case called the residual polynomials. This is just a somewhat more general form of it. See, we can sometimes think of monic polynomials. A monic polynomial would start with z to the n. So if you divide out z to the n and then take the limit to infinity, you get 1. So in a sense, we can say a monic polynomial is normalized at infinity. We're doing this new version where we normalize at some other point, x star. So what that means is essentially you pick a point x star, you put a pin in the graph, x star comma 1, and you say every polynomial has to go through that point. And so then we say, well, what polynomial has minimum value among those everywhere in E? So again, supreme norm, we're trying to say it's the smallest possible in E, but we constrain the problem by making it go to this one other point. So if you don't have a constraint, then the zero polynomial trivially solves it every time. Well, we get a new Green's function. Strictly speaking, the Green's function always has 2 arguments. It is as a pole, a point where it goes to infinity, and then it has just standard input. And so we usually fix that pole. And in the previous cases, we were fixing the pole at infinity. But instead, we can fix the pole at this x star. And then what happens is that near that x star, it's still logarithmic, but it's logarithmic of 1 over z minus x star. So it goes to infinity there instead of at infinity. That'll be its only pole. One nice property is that these are symmetric, meaning if you want to move the argument, switch argument in the pole, you get the same value. So instead of evaluating this function, this function at infinity, we can evaluate the regular Green's function at x star. So there is a similar alternation theorem for residual polynomials. It's still an alternating set, but it does not alternate near the normalization point. because our norm couldn't be more than 1. It's pretty easy for any degree greater than 1 that you're gonna be able to make it smaller than that. So you have this one normalization point where it's equal to 1, and then it'll have the max on both sides of it. And a minimum over on the other side. You can see this example, the set is -1 to 1, union 2. So there's a big gap here in the middle. You can see it has maximum at 1 and 2 and minimum at -1, and they're all the same value. All right, so capacity, similar thing. We have capacity comes out of the Green's function here, infinity. So if we want to say was capacity at x star, it is the exponential of negative g the value of x star. So the regular Green's function, plug in x star, and you get capacity. And it works the same way. And then the Whittam factors, this one's a little surprising because you would expect it would just be the residual norm times capacity, but it's not. It's actually capacity, it's CE to the n plus CE to the negative n, CE of x. But with that definition, you can get the nice property that the Whittam factor at x star, if you take x star to infinity, you get the old Whittam factors. And it has some other properties that carry over nicely, but you have to use this definition, which is a little less than obvious. One little wrinkle here, when we're trying to get the bands here, we're trying to do the trick before where we maximize over each gap, is that since we only have we could have only n-1 zeros in the set, because we don't have to have n+1 alternating points, we have to have n alternating points, so there are only n-1 zeros accounted for. Could be another zero way outside E, which would mean there's an unbounded gap. We have to maximize over this. Well, what if the function is monotonic? It keeps increasing on and on. It won't go to infinity because it only has one pole, but it might have a maximum at infinity. And so we have to define the derivative at infinity. And here's the definition we're using. And so if that is 0, then we consider infinity to be another critical point. Once that's done, everything's pretty much the same. The Whittam constant, the irregularity coefficient, they're just by summing up critical points or irregular points of the new Green's function. And so we get the exact same results. The residual case, for a semi-regular complex set, we get 2 exponential of IRE less or equal to less or equal to 2 exponential of PWE plus IRE. E's an interval, then we get 0, and so the limit is exactly that. So what's left to do? Well, we want to know, like I said, one of my main questions is, when do we need this semi-regularity, or do we need it? Would it be possible to show these bounds exist for all irregular sets, or some similar amount? The converse, we know that if W and E, if our, say here, yeah, we know if IRE is infinity, then W and go to infinity. Is the converse of that true? If E is compact and not semi-regular, would the upper bound go to infinity necessarily? If E is regular and the Whittam constant is infinity, then norms go to infinity. Is that true? It's basically a lot of converses we're on here. We also started working on minimal error functions, rational functions, which is to say a polynomial can be likened to a rational function with a pole at infinity. If we move the poles somewhere, or if we have multiple different poles, there is some work on this already, and I would like to see if we can extend this to irregular sets. All right, that's everything. Thank you.
Thank you. Well, now it's time for questions.
No,
she's
Sarah
clapping.
is clapping. Okay.
There's chat. Oh. Thank you, Jeffrey.
I would be happy to ask some questions.
Sure.
Go ahead.
Good. So, first of all, Robert, I've had the pleasure of reading your thesis here over the last few days. And I should say that I very much enjoyed reading, especially chapter 6, because that had some interesting new points to me. So that's also where most of my questions will be. So one of them you actually already answered in your slides, but I have another one. So if you go back to, I believe, slide number 14.
Sorry, may I have a brief break? Just run down.
Yeah.
All right.
Okay, okay.
Numbers I was looking before. You were counting, Jacob, or? Doesn't show the number.
Doesn't show the number. Is this the right one?
Next one.
Yes,
that's the one.
Thank you for waiting.
No, no worries.
So what were you asking?
Yes, I will return to the questions. So basically, I have a question to the proof of the upper bound and also to the proof of the lower bound. So let's start with the upper bound, and I believe we're on the right slide. So you estimate the sum of the integrals, and you take the maximum over the gaps.
Yes.
You say that this is either a point in the middle or an endpoint. Well, not in the middle, but a critical point. Now the gaps are open, right?
Well, yeah, but we can do the closure of it and it works the same.
Okay, but do you know that if you take the closure that you have continuity of the Green's function?
The Green's function continues on E naught complement. We are in a gap.
So one of the reasons we considered the semi-regular sets,
Yeah.
because that's exactly the type of sets where the
Right.
green function is continuous everywhere.
Yeah, that's true. Yeah, if there were because yeah, you could have in theory a case where the bound is it just goes to infinity at the edge, but that would mean it would be discontinuous there, which would mean it would not be closed, the no longer be closed. So
Mm,
that is one of the things where we took out some irregularity, we'd have to hold this question.
yeah, I'm not so sure it can go to infinity, but I mean, it could be that you had discontinuity and the value at the endpoint would actually drop down. That would be my concern.
Right, and I think as long as we have the semi-regularity, that won't be an issue.
Yeah. But even if you, what was that an assumption for this result?
That E naught is closed.
Right, that's the
The
symbol.
regular part of E naught, the part where it equals 0 is closed set.
Yeah, yeah. Okay, I was wondering if one could also, I mean, there are some properties of you show that the potential is lower semi-continuous, so the Green's function should be upper semi-continuous. So one might be able to work around with stuff like that also.
I have thought about that as this lower and upper semi-continuous show up a lot in the literature. It didn't seem like it was necessary for these results, but it may be a way to work around where we don't have semi-regularity. So that is worth looking into.
Yeah, but once you have isolated points, I agree to that. And if you end up in a fat part of E, I mean the Green's function, regular part, the Green's function will just go to 0, so no problem. Okay, good. Thank you. Next question is if you go ahead 3 slides. Okay, good. So now what you write in your thesis, you don't quite write it here, is that once you have an isolated point, you can have at most 2 bands of the En set that's approaching this. You can have at most 2 zeros that are approaching it.
Yes.
Why can't you have more?
Because, well, it's basically because there are only 2 directions that it can come from that I remember having this question and I thought I wrote it in the thesis, but I think because each one has to anchor a band that's approaching it, so I don't think you could have 3 different bands. I think they would overlap in that case.
But if you instead of thinking of an isolated point, think of a point inside, say your E0 is the interval -1, 1. If you think of a point inside, I think you can have more zeros that approach the point, right?
Yes, that works for that case. If you had that in the case of an isolated point, I feel like that would, in the inequality, that would cause it to blow up. I think this would be a violation.
That's exactly why you would have the problem in the proof if you had, say, 2 from one side.
I distinctly remember dealing with this. I can't remember exactly what my explanation was, but it felt like that was.
So if you consider these En sets, what do you know about the endpoints?
They have opposite signs. They take the Chebyshev norm at either end.
Yeah, but how are they related to the set E?
How would they relate? I'm sorry.
Yeah, must they be points of E or could they be outside?
No, they would not necessarily be points of E.
But if you have 2 En bands in En that are close to one another, then you can say something. Either the left endpoint of one of them or the right of the other will be inside E, right?
One of them needs to be inside E. Get a band that's centered around or it's not centered, but it contains an isolated point. I think if the bands would be distinct, would be disjoint. So I don't think they would necessarily, if they're around isolated points, I don't think they would contain any other point of view besides.
So what I mean is the following. You consider the set En, so the bands in En, and you have the two bands that are closest to the isolated point from one side.
Well, there would also be the band containing the isolated point. But I think each of those bands would have to have its own isolated point that it narrows around. That would have to, as you increase the degree.
Perhaps I should phrase my question slightly differently. If you have two isolated points next to each other,
Next, you just adjacent. Okay.
there are no other isolated points in between.
All right.
Okay. Then each of the isolated points sits in an En set.
Yes.
Could you have an En set in between, in the gap in between?
I don't think so. I think this property here on the slide I'm showing now, that I think that would cause it to just blow up there. Basically, I think it would, as you increase the degree, it will get larger because there's no isolated point to bring it down to zero. And so because if it were another band of En in between, there would have to be a zero in that band. And if that were the case, we have another zero in between there. I don't.
So what would that violate? I think it would violate a basic fact for Chebyshev.
Yeah, I'm trying to think of which.
It would violate the alternation property.
That's what I was trying to figure out how exactly that follows. I think you're right, it would.
So for these En sets, if you look at two that are next to each other, then either the left-hand point of one of them or the right of the other will be in the set E.
Yeah, they would have to have the same.
And since you have these two isolated points and you already have En sets containing those points, you cannot have anything in between. I think.
Yeah.
But this was a point where I had to think intuitively. You don't think that you can have more than because it's an isolated point. But I think that the argument really here relies on alternation.
We make it work. Adding a comment
Okay.
to make that clear in the.
Yeah, I know,
presentation.
Yeah, I can do that, because I know I remember grappling with that when I thought I'd written in an explanation there, but maybe it was not clear enough. I don't have the document in front of me right now.
Okay, next question. If you move on to, let's see, 5 pages ahead, or maybe.
Yeah, more questions, yes.
Maybe
Okay.
6.
Okay.
6 pages ahead.
Yeah. One back. No, let's see. After the summary, so one forward. Yeah, good.
Okay.
So here you have the setting where E0 is connected, so it's an interval. And my question is how does the green function behave outside E0 then? As you approach the endpoints of E0, how does the green function behave? So it's a function that goes to 0, but how does it go to 0?
How's the green's function? How does it go? It's 0 on the interval.
Yeah.
If it were coming vertically, it would then have a local minimum in the sense with respect to y.
Yeah.
At the endpoints, it would be 0, and then it would start increasing as x either increases or decreases
Yeah, and how fast will it increase?
as it leaves. How fast will it increase? Well, the Bernstein-Walsh inequality gives a bound on that. It would increase that's the polynomial, not the Green's function. I mean, I know once we get close to infinity, we know it's approximately logarithmic, but it takes time to get up to there. So I don't think we have I don't know if we have a local description of just what happens right at those endpoints.
It will increase like a square root.
Square root.
Yeah. And that also applies to many more complicated sets. But once you just have finitely many sets, the green function at the endpoint will grow like a square root.
That would make it.
And I mean, for the interval case, you even have an explicit formula for the Green's function, so you can check it.
Yeah,
Yeah.
yes, there is for the interval, it's square root. I can't remember, I haven't memorized it, but yeah, it's a square root involved, I know.
But the reason the reason I'm asking to this is that you want to know whether or not the irregularity coefficient is finite. You have a number of isolated points that are approaching the endpoints. And in this case, you can actually say how fast or how slow they should approach the endpoint because you know the behavior of the Green's function for this sum to converge or diverge.
That's true. If it's an interval, yes, we do have that explicit formula. You're right.
Yeah. So this was something extra that one could add. So you know quite explicitly how fast the point should approach the endpoint for this to be convergent or divergent, since you know the behavior of the Green's function.
All right.
Right. So this theorem that says Re finite would be rephrased by saying the distances to the set square root converge.
It's an interesting idea.
Yeah. Okay. Final question from my side. So you mentioned something about further directions. I can think of one further direction that you will have the chance to comment on. What if you leave the real line and you go out in the complex plane?
Oh, that's a fun question, isn't it? I don't have any easy answer for. In particular, the alternation theorem that we've relied so heavily on does not really apply once you leave the real line. But yeah, I haven't really figured much out about that. There is research, I believe there's some involving Jordan curves, but that is not something I've done much looking into yet. So that would basically be another project altogether, I think. That's not saying I wouldn't be interested, but certainly not something that I can make much progress on right now.
I was simply curious.
So am I.
Because it's the next natural step. I mean, one first step could say these isolated points could approach from each side, but potentially they could also approach from certain directions in the complex plane, and it might be interesting if one could say something there too.
Sure.
But I also agree that once you go to the complex plane, you can forget about alternation, and well, it's a fact that life becomes harder.
Yeah, there is definitely something to look at. I think if I were open-ended, I think the next thing I would look at is the rational functions, because we did do a little work on that about a year ago, and I sort of hit a dead end and switched back to the Chebyshev polynomials. But yeah, we did like maybe one or two proofs, and so that's something that would definitely be the next thing I would look at if it were up to me.
No, I agree. This is a more that's an easier path to follow first. Good. Thank you very much.
Thank you.
Yeah. Any other questions? All right, then we're good. the committee will stay to chat for a little bit.
Rob, one more hand.
Yeah.
Okay.
Yeah.
Thanks, everybody on
And you
Zoom,
on the Zoom?
except
Yeah,
for
except for
Jacob.
Jacob. Bye, Sarah. So, yeah. So we need people to leave,
I don't, do I have?
except for Jacob.